Hey, welcome to what may be our last session for the year of Flipped Classroom for Calculus, Section 5.2, Volumes of Revolution by the Shell Method. This is Session 38. Up to now, we've found volumes by summing up the individual volumes of cylindrical disk across an interval on the axis of rotation. But we can also find the volumes by summing volumes of cylindrical shells that grow outward from the outward axis of rotation. Think of a roll of paper towels where each one wrap of the towels is a shell. If you add all those shells together, you would get the volume made up, okay? So you can either do this horizontally or vertically. Here's a short animation that'll show you what's going on. Okay, so we have a graph, rectangles, and we're building up these solids. What we're doing is we're revolving this around the y-axis, and they're only showing you half of the circle, the shell, so you can see how the shells grow. See how the height of each shell is actually the function value of this curve. Now they're adding in the other half, and you can see the solid that's formed. Okay? Pretty cool. You want to run that? I'll show you again. Here we go. This is our graph. These are the function values. Those would be the heights of the shells. The value of x would be the radius of rotation for each shell. And dx would be the thickness of each shell, the thickness of each rectangle. Okay? All right. Going back, okay, here's another a graphic. Again, like I said, we have a function f of x. We're going around the y-axis. F of x would be, this is one shell here. F of x, the function value would be the height of the shell. The radius of rotation from the axis to the point that we're concerned about would be x. 2 pi x, if I took this shell, this is a ring, just like one wrap of paper towels, and I cut it so I could stretch it out into a rectangle, then 2 pi x would be the length of the rectangle formed when you cut one shell and stretch it out. X being the radius of rotation, 2 pi x, 2 pi r, circumference of a circle. And of course, dx would be the thickness of each shell. So imagine, if you will, many shells, and we're just going to add up the volume of each cylindrical shell, and that would be 2 pi x, okay? That would be the length of our rectangle. F of x would be the height of the rectangle, and dx would be the thickness. Put them together to form one little circular cylindrical shell. And we're going to do that from A to B on the x-axis. Notice, when we go around the y-axis, everything is in terms of x. When we go around the x-axis, we'll see that everything has to be in terms of y. Okay, here's a sample problem. The red curve is y equals 2 minus x squared over 4. Okay, so this is our f of x. The limits of integration on our x-axis are from 0 to 2. I've tried to shade in the region we're rotating, but that's the best I can do with the different technology that I have. But it's really going to be everything underneath this red curve bounded by this dashed line, this axis, and the y-axis. And we're going to revolve this thing around the y-axis, okay, around the y-axis. So basically, our limits of integration would be from 0 to 2. The volume, using our formula, I took the 2 pi put it on the outside because that's a constant, would be x. That's the radius of rotation. I've got a yellow rectangle here. Imagine this would be one shell. Here, the radius of rotation would be 0.75. Okay. The height of that shell would be f of x. Okay, there's my f of x. And the thickness of the shell would be dx. Okay, so just to integrate this, to let you know, we're going to let u be 2 minus x squared over 4. We're going to integrate that, and when we integrate it and evaluate it at 2, 0, we get the volume equals 6 pi. Notice that I integrated this using u substitution because it's much easier, okay? Now we can also go around the x-axis. When we're revolving around the x-axis, the process is exactly the same, only everything needs to be in terms of y. So if you had an equation like y equals x squared, you need to solve it and make it x equals the square root of y. So our volume formula just becomes the integral of 2 pi y axis of rotation. That would be the radius of rotation, I'm sorry. F of y, again, f of y would be the height of the shell, dy the thickness of the shell. And we're going from C to D. I've already said this, if the function is given in terms of x, solve for x in terms of y. And here's a sample problem. Let's see if we can lay this out. We've got the line y equals 2 here. We've got a function x equals the square root of y right here, and another line x equals negative y. This blue region, okay, I'm moving my mouse around it now. I tried to shade it all up. This should be included also, is the region that we're going to revolve down here around the x-axis, okay? So if we're going around the x-axis, everything needs to be in terms of y. Okay, our limits of integration, okay? Well, the limits of integration, how many of these shells are we going to have? We're going to have these shells from here, the origin, up to the line 2. So it would be C to 2. C equals 0, D equals 2. Okay, now here's the function. The way you do this is pick a rectangle parallel to the axis of rotation. So this yellow rectangle is parallel to the axis of rotation. Try to figure out what its length would be, okay, because that would be the height of the shell that's going around this axis. In other words, imagine a roll of paper towels horizontal on a paper towel holder. The height of the length of those roll of paper towels is this value of the rectangle. So clearly, So clearly this part is just the square root of y, and then this part you might say is negative y, but if we're talking distance it has to be positive y. So our height is going to be the square root of y plus y. Does everybody get that? Okay. So if we go up here, here's my volume integral, 2 pi integral, here's my y raised to the 1/2 square root of y. I'm multiplying it times y because that's the radius of rotation. And here is the y that I've made positive, and that has to be multiplied by y, the radius of rotation. Okay? So cleaning it up again, I get y to the 3/2 plus y squared, the integral of that, times 2 pi. That becomes 2 pi times y to the 5/2. I see that I left, this should be over 2/5. It's times 2/5. Sorry about that error. Plus y cubed over 3, all evaluated at 2, 0. Here we have the 2/5. So the volume is going to be 2/5 square root of 32, because 2 to the 5th is 32, and take the square root of that, plus 8/3. That's what 2 is when you insert it into y cubed over 3. The second part, the f of c, if you will, is just 0 because y would be 0 and these values would be 0. So we clean this up, we find a common denominator, and when it all comes out in the wash, what we get is 16 pi over 15 times the quantity 3 square root of 2 plus 5. That would be the volume of this solid that's rotated about the x-axis using shell method. Okay, here's the length. Again, I told you, here's the function, here's the other function. Okay, so our basic steps for using the shell method are as follows. Draw the region to be rotated. Okay, you can either graph it or draw it. Determine which axis will be the axis of rotation. Usually they tell you that in the problem. Draw a representative rectangle that is parallel to your axis of rotation, which would represent the height of each shell. This will help you get your thoughts together on just what functions you need. Determine the upper and lower bounds of integration, and then integrate using either the formula v equals 2 pi integral of f of x, that's the height of the shell, x radius of rotation, dx thickness, okay, from A to B. That's if you're going around a vertical axis, or v equals 2 pi f of y, height of that shell, y radius of rotation, dy thickness of the shell, from C to D if you're going around a horizontal axis. So let's work on some problems. Page 433, 434, 1 through 36. Peace.